good evening, wherever you are in this world. I'm glad to be here and give you some my insight on how to work with indexes. That's what we're going to talk about today. All right. Okay. I don't quite live in Austin. I live about 75 miles to the west-northwest of Austin in Texas. I speak Texan, so I hope y'all understand me, and I have a lot to cover today, so I'll speak fast, even for a Texan. And I live in a little village called Sunrise Beach, and you can see it's aptly named in the picture there. There's my contact information, and we'll get back to that later. What I really want to do is talk about, I don't have some of the three-letter acronyms that a lot of people do. I'm not an MVP. I'm not retired yet. I did get, when I was in Air Force, Lieutenant Colonel, so there's my LTC. But in reality, I have a four-letter acronym, GEEK, and that's usually with what I talk about myself, and you'll see how geeky I get in this presentation. So in former times, as I said in the intro, a rocket scientist, I was an Air Force fighter pilot and test pilot. I freelanced for PC Magazine for a few years. I was a CTO for an insurance company for 9 years, got a new boss. Shortly thereafter, he asked me to part company, which I was really unhappy about. However, one of my contractors gave me a call and said, Mike, could you work for 2 days? Ended up being 2 years. It got me back on the technical side of it. I love SQL Server. You wouldn't believe how much I do it, especially the performance tuning part of it. And so ever since then, I've been working in SQL Server since 6.0. I'm right now a part-time database consultant and trainer. I used to blog on logicalread.com, and now occasionally with Steve Jones on SQLServerCentral.com. My goal in life is just to dig deeper into optimize your black box and figure out how it works. So was I really a rocket scientist? I'm not going to go through all that, but people have asked me that in the past. So if you look at that, the credentials there, I think you'd probably say I do qualify. The picture in the lower right hand is a rocket motor when I was at Purdue getting my master's degree. And obviously not a flyable motor, but it was testing performance characteristics of propellants at unusual scenarios. And basically, I'm just a geek from day one on. Today, the presentation, T-SQL demos, index utilities, and database backup files can be downloaded at that site there. And again, it's tinyurl.com, rocket indexes. You may need to map the drive letters for the DB restore. However, I think if you just once you get that written down or taken a picture of it, if you just listen and then later on review the slides and scripts on your own time, I think you'll get a lot out of this presentation. At least I hope you do. There's the Dropbox location. The one script I'm going to be going over primarily is cover and index column order.sql, but you can see there's a PowerPoint presentation. There's a backup of VentureWorks 2017 Big. I'll talk about that in a second. There's a way script to create the big version of the two tables from VentureWorks 2017. And then there's some missing index utilities that I'm not going to talk about today, but they're very applicable for working with indexes. So just as an overview, think about how do you create indexes? Do you take the index wizard recommendations? Do you really look at column selectivity and ordering? Do you consider duplicate and near duplicate indexes? How do you know you made the right selection? Do you just define one column? And what about other columns? Do you put them in the index definition? Do you put them in include clause? Are you concerned about the width of those columns? Because the width can make a difference in the size of the index. We're going to talk about some of this in the next 50 minutes or so. And so with that, let's get started. This can be a lot of material. I don't have enough time to talk about it. I could talk about this for 3 hours and still not repeat myself. So again, listen, download the scripts, try them on your own. You get much more out of this with the secondary, tertiary review. So let's look at the script cover and index column order.sql. But first, let me switch screens here. Here's the script to create the VentureWorks Big, and all this script does is create two tables. It creates a sales order header big and a sales order detail big. And so sales order header in the original database was about 31,000 rows. Now it jumps it up to 1.3 million rows. Sales order detail was 121,000 rows, jumps it up to just under 500,000 rows. I have another script that I run that gives capacity of the and shows the size of the indexes, and you'll see that in some of the review columns. Okay, so let's get started. I always start whenever I go to a new client or anything, say, well, what version am I running? You can see I'm running 2019, the latest C cumulative 18.8, and I'm developer version on my own box. And then I also messages. I've also done it. So I have a clean version of VentureWorks 2017 Big. I've already restored it. And so if we go over here and look, and you look at VentureWorks 2017 Big, it has two new tables. It has sales order header Big, and it also has sales order detail Big. But if we look at sales order header, if we look at the indexes, these are the same indexes that come with VentureWorks 2017 sales order Big. Anyway, so those are the indexes. With that, let's get started with a query. So, and let's see, I have everything turned on. So all this is a select statement from sales order header Big. Remember, that's about 1.3 million rows or so. Sales order ID, revision number, territory ID, modified date, where territory ID is greater than and a territory ID and status is equal to some value status, which you can see is defined above. In this particular database, any territory ID is greater than 5 or non-US. So this is a very simplistic query. I run it twice just so that I can get rid of the fiscal IOs. And if you look at the execution plan, if we come back over to messages, you can see there was one fiscal read, but in the second version I ran it, there's 0 fiscal reads. So let's go back to the query plan. You can see a suggested index is there. We'll talk about that in a second. And you can see, let me bring it up into the picture. Come on, stay. It's a clustered index scan. And then you can see there that there's a predicate. The predicate is on territory ID and then on status. Let's talk about predicate, because sometimes you'll see a predicate, sometimes you'll see a seek predicate, sometimes you'll see both, all of the above. The seek predicate takes advantage of the ordering of the data that's in your B tree for your index. The predicate then, after that result set, then the predicate filters it further with, in this case, it's by the territory ID greater than at territory ID and the status greater or equal to at status. So in this query, we have an equal and we have a greater than. And so let's come down and look at some of the numbers. We come over here and look at the cost. It's 22.25, and it took roughly it had 29,295 reads, and it took roughly 297 seconds. Well, it varies on my computer depending on what else is running on my computer with that. So there's a difference there. But okay. So we looked at, and we have the values there. So let's go back and let's run the missing index. Now I tend to, when I write indexes, I like to have usually IX underscore the table name, and then the various columns that are in the index definition, not an include clause. So in this case, we have status and territory ID, it's in the name, and then we include the revision number and modified date. And this is a cover and index, and that's all we're going to work with today, primarily is cover and indexes. And so if we run that, and then we run the capacity check, you can see that indexes don't come free. You're paying about 26 meg for this space for that additional index. And if you notice in my slide or up there, I had data compression equal to row. If you don't have data compression equal to row, if it's equal to none, it's about 30 meg versus 26 meg. So there is a savings in row compression. I use it everywhere, as Monica said yesterday. So let's run now the query again, same query. And look at the execution plan. Now we get an index seek. And now you can see it's a seek predicate. There is no predicate. And it took advantage. Notice it put scalar or status first, and then it put the territory ID second, even though the where clause had them. If you look up here, the where clause had territory ID first. And that's a reason for selectivity. And if we come down and look then, instead of the, so now we're down, instead of an index cost of we had earlier 25. Now we're down to 0.26. And if you look, we also had 264 or 5 reads. Again, it depends on where you start and mix extend. And this number will vary a little bit as you run the same scripts. But anyway, it's significantly less than 29,000 logical reads we had earlier. And then you can see it took 110 seconds. Running slower. I think the streaming software is causing some of my queries to run a little bit slower than anything. So what happens if we change the non-clustered index and do territory ID first, followed by status? And before we do that, I want to switch back over. No, I don't have that. Okay, so switch back over, and if we look at the table, you can see that if we organize it and do a select by the status, territory ID, and modified date, it comes down and you have status of 5, and then the second column, territory ID, is the status of greater than 5. So if you go greater than 5, then it can the predicate seek or seek predicate can go directly to the lines in the index. They don't have to worry about it. I don't know if that's real clear, but if I use these type of tools to help me visualize the data so that I can, the queries like this, visualize the data so I can see what's going on and try to understand what the optimizer is doing. So let's come back over to here. And let's see, did we run this? We'll run it again if we didn't. Okay, and now you can see that the size of the index is roughly the same. And again, about 5 more meg to if you don't have the row compress. And we run it again, and we look at the execution plan. We still have index seek, but now we have a seek predicate based on territory ID because that was the first column, and then the predicate is on status. So the data is not organized in a greater than, with that greater than that we have for territory ID. It's not organized so that it can actually take advantage of status in the B tree, even though status is included in the B tree as your second column. So I hope this is starting to make sense, but now we're instead of 0.2, we have a 1.14 for query cost. And instead of that small number of logical reads, we're now back up to 2024, and it took 250 milliseconds. So let's go back and say, well, what happens if we have status as our first column? Because we've already seen that's what's suggested, and territory ID is in the include clause. So we'll drop that. And again, it's still, the index is around 26 meg. And now if we run the query again, same queries we've been running all along, we get an execution plan. It's still an index seek, but we still have a seek predicate on the status, and then we have a predicate on territory ID. And with a cost, query cost 0.4, that's about double what we had with the recommended index. And then also 425 reads. You can see that's a lot less than we had from when we had territory ID first, and 109 milliseconds. So if we go back and let's drop this, and we go back and just look at a summary of what we just looked at. I'll tab. And this is again showing status and territory ID and showing how the data is organized. So we first in the optimizer, since I used to seek predicate on the recommended index, it went to status of 5, goes all the way down to find something greater than 5, and you can see there how it's organized. And then if we look at what we were trying to do, you can see the 22.5, the recommended index is 0.265. When we had territory ID first, it was 1.4, but when we had status first and then territory ID and include clause, slightly more in query cost, and again, almost not quite double, but double in the number of logical reads. So what is what do you gain by putting territory ID and include clause? Well, you gain a little bit of space in your root and your intermediate levels of your index, because territory ID is still stored down at your index page level. So that's query one. Let's go back. Let's go to scenario one. Let's go back to there. And I did drop that, didn't I? Oh, I love the new version of when if exists. That really is nice. Unfortunately, half my clients are still in 2012. Okay, so here we have another query where we've added in a third column. And we have essentially almost the same query, which before: sales order ID, revision number, territory ID, modified date. And then we have modified date greater than equal to start date, modified date less than end date, status equal to at status, and territory ID equal to at territory ID. And we'll run this twice again, just to make sure that we don't have any physical reads. And we come down and we look at the execution plan. And execution plan for this. So we have a clustered index scan. So we're probably going to have about 29,000 pages scanned there in the logical reads. And let's go and check that. See, and sure enough, there's 29,295. Took about 265 seconds. And we come back over here and we have a query cost of 22.38. And we look over here and we have just a predicate. Now the predicate has modified date, and then it has territory ID, and then lastly, our status, and then it's checking on territory ID at the end. Essentially the same order as we had up here in the where clause. So just right now, I hope you're starting to see that the where clause usually defines the columns you probably want in defining your index, and then anything else like in your select part of the clause, anything that's not included in the where clause, then that probably needs to be in the include clause. Think along those lines. So it's not absolutely all the time true, but it is true for a lot of cases. Again, we had a cost of 22, which is roughly what we had before. And we still had that big logical reads where we scan the whole table. Okay, so now, again, it has a recommended index. And this is the optimizer came up with a strange result here. And again, you can see it's about 26 meg in size. And now if we run that same query we just ran earlier, and we have now an execution plan where we have the index seek. And we have a cost of 0.088. This is not the one with the strange one. It's the third scenario that has a strange one. So we really dropped down. So we had 0.088. We're at 22. We only have 4 logical reads. Sometimes it's 5. Yeah, it depends on where the index starts in the mixed extent. And then execution time of 0. So just for fun, again, we come up here, and now let's go back and look at our execution plan. We have the seek predicate is based on territory ID, and then or status, and then the territory ID, and then the modified date. With the modified date also, so everything was covered by the seek in this particular case, by the seek predicate. If we come back over here and just for fun, now it's reverse status and a territory ID just to see what happens. And if we run the same query over again, I'll show you all the results in the table at the very end of this. And now we have index seek again. And now the territory ID and the status are reversed, but it's still essentially the same index we're doing, because they were equal in this case, not that we didn't have a greater than. It didn't matter which one came first, and we still have a cost in about 0.088. And in this case, that we had the 5 logical reads. So we can deduce a lot of things from this, that if you have equalities, it doesn't matter which one comes first in the where clause or in your index. But if you start to have not equals or greater than or equals or less than and equal or less than's, then it may make a difference in the order. So let's do a little cleanup, and then let's go back and relook at the results again. And we switch back. Okay, this is the scenario 2, and we have our data. And so we started off with the clustered index scan where we had 22.08, and regardless of whether territory came first or status came first, we had roughly the same logical reads, same performance, and the same number of rows returned. So going back, we're running good time. I guess I'm talking too fast. Okay, so let's look at a different query now. Okay, this one is roughly the same as before, except remember in before I had territory ID equal to @territory ID. And this one, it's now territory ID is not equal to territory ID. We'll run it twice to make sure we shouldn't have any physical reads, but I'm not going to chance it. Execution plan, we come down. We have a suggested index. We have a cost, and it's 22.4, roughly what we had before. And now we have no seek predicate, but we have a predicate that's based on modified date and status and territory ID. And notice the status is switched up front, but that's what it was here. Same order as what's in the where clause. And the optimizer doesn't seem to really care when it's doing the filtering. It just does it. So again, we had 29,295 reads. Again, is scanning every row, all the pages, and then we had the clustered index or the predicate, no seek predicate. Now, the recommended index, if you come back over here, if you look at it, it's based on status, territory ID, and modified date, and it includes revision number. And why don't we have sales order ID? Because that's part of the clustered index, and the clustered index is automatically included in any index definition. So let's not worry about that. Let's come back over now, and did I create it yet or not? I don't remember. Let's try it. And again, you can see it's roughly the same size as before. They're all about 26 meg. Now let's rerun the first query again. This is the one that I thought was kind of interesting, and I don't have a good excuse for why it comes out this way. And there's the execution plan. You're going, wait a minute, what happened? We have the index seek on the non-clustered index, or the one we just created, but it's joined to all this stuff over here that doesn't appear to have any connection with the table. And this puzzled me for a long time. Okay, so we have the clustered index seek. We look and it has a seek predicate. Notice though, it pushes modified date out to the predicate, and in the seek predicate, we're on status and territory ID. So what's going on here? It's not quite what I expected. And so we have a query 0.308. And if we look at, we had 2 scans going, well, where did the second scan come from? But we're down to 378. So the logical reads are a lot less, and it took about 15 milliseconds. So the big question is, why did the optimizer come back up here and look? The optimizer, it recommended status and then territory ID, but let's go through and redo the query, and let's put the status and then the modified date, then the territory ID. And I do have a reason in the back of my mind for doing this. So let's just run that. And now the same query again. And we look at the execution plan and going, wait a minute, what happened to all that junk we had in the previous one that Microsoft recommended over the Mike Byrd recommended one? And you can see now the query cost is down to 0.2, so it's a little bit about half of the original. And if we come over here and look at it, we have seek predicates. In the predicate, we're on the territory ID, and the seek predicate, we have status and then modified date. So why is that? Well, if you look at the index and the way it's ordered, and I have a query over here where I ran it, is that it can, using the B tree, then the seek predicate, it can go straight to a status of 5. And then since we had not equal to 5, then it goes everything above it and everything below it. And that then, if the third item is modified date, the third item then would be the dates sorted in the third order, which then has to do a complete seek through all that, and that's where you get or scan through all that, and that's where you get the predicate. But if the modified date is second, then for a status of 5, the dates are all in order for a status of 5, and then it can do a scan on the territory ID. That's what caused this one to be better. And I hope that makes sense. So we got it. And if we come back over here, we can see we had 24 logical reads and execution time of 0, which 0 doesn't mean really 0. So now, and notice we had both indexes active at that time, but it still took the modified date, status modified date. Go back to here. If you look at that, look at the object, it's this status modified date and then territory ID, which is the one we did. So let's drop that and let's just look and see what happens if we put modified date first in front of status, just to see what's going on and see again. And again, this is the geeky part of me going, wow, why does Mike do all these crazy indexes? Because I just want to see what's going on. So now it goes back and gives the recommended index, which, if you remember, the recommended index was not the right index. The right index is the one where modified date comes before territory ID. And we're back to, okay, so this was an index seek, and you can see under the seek predicate that the modified date is there, but then the predicate has both the status and the territory ID of that. And that's because the things aren't ordered behind modified date correctly, or correctly as far as the B tree goes. So, oh gosh, does this make sense so far? I hope. And you can see that it was still around 26 meg. So I did one more query. I wanted to see what happened if we know that if we make a query that's on status modified date, and remember the one we had before had territory ID up here, but I said, what happens if we push the territory ID down to the include clause? And so let's do that. And let's rerun the same query one more time. And we get up here, and lo and behold, it's the query cost is, again, 0.2 roughly. And we have the seek predicates down below and the predicate of territory ID up above. So going back to looking at the table for scenario 3, go away. We're going up. We can see that for the first one, we have this clustered index scan. And then for the second one, we had the recommended index, which wasn't good. But then if you look at the third one, which I used the Mike Byrd index, is 0.95. And then lastly, and I can't get the screen to come up. Let's go back. And lastly, essentially the performance was the same down here as it was for the second one. So in this particular case, it didn't matter where the territory ID was in the index column definition or in the include clause, because it was used both times in the predicate, not the seek predicate. So switching back. let's change gears and let's take a case where I don't need to restore it because we're back to pretty much normal. And let's look at a case where we have a single table query with a join to another query. So we're going to join from sales order header to sales order detail big. And then we're also going to join to production big. And so if we run this query, we're going to get execution plan. You can see it's asking for index. And if we look over here on the sales order header big, you can see it's doing a clustered index scan. And that's what, and if we come down, you can see it's doing an index, non-clustered index on sales order detail big, and it's doing it on the product ID. However, if you come a little bit further down, it's doing a key lookup. And key lookup to me is a sign that maybe I might be able to prove the query a little bit more. And then product is joined up here, and it's a clustered index scan on it with a seek predicate. So that ends up with an overall cost of 48, about double what we had before. And if we look at the, we have almost 13,000 reads on sales order detail big. We have our standard 29,295 logical reads on the sales order header big, and we have 2 logical reads on there with a time of roughly 600 milliseconds. So we go, okay, so normally, as I said before, when I look at an execution plan and I see a key lookup, I look to see, well, how many things is it asking for? And in this particular case, it's only asking for unit price extra over and above. So that, which means that in this index here, if it had unit price, it wouldn't have had a key lookup. So why don't we look at what would happen if we added unit price to the product ID under sales order detail? But we're not going to do that right now. Let's just go ahead and run the suggested index that they had suggested. And if we run that and then we run the same query over again, and then look at that. Well, we dropped the query cost almost in half, not quite. And if we look at over here for sales order header big, now we dropped it down to 40 reads. We still have 13,000 reads on sales order detail, and we still have the 2 logical reads on product. And the CPU time dropped down to 31 milliseconds. So it really helped taking out that roughly almost 30,000 logical reads on sales order header big. But what happens then if we go back and redefine the sales order detail big product ID, and now we create a product ID, but we include the unit price? In other words, we're going to try to make the product ID cover this particular query. So if we run that, and then we run again, I just like virtual presentations because I can't see if y'all are awake or asleep or not. That's one thing that really bugs me about this. Now, the unit cost is now down to about 1.06. And if we look at the logical reads, we dropped sales order header big is down 37. Sales order detail big, remember, was a big number up in the thousands, and now it's 432. And CPU time is 31 milliseconds. So that's all defined here. So the question again is what columns to include when? To me, when I go back and look at a where clause, those are the columns that I consider for each of the items for each table that maybe should be in the index definition. And if not in the index definition, maybe in the include clause within that extension. All right. we've learned a lot here, but I don't know if you've really learned a lot because it's overwhelming how much information I'm giving you so fast. I strongly recommend you download the scripts and you try running it on your own. Okay, I'm going to skip over some things just from a time point of view, and we're going to go down here and look at, and I have a completely different what we've been talking about. So let's look at covered indexes for update statements. So I'm going to create a new database called index test, and in that test, I'm going to create a sales order detail, and I'm going to insert all the data that's in sales order detail into it. Okay, and so then if let's just do a simple collect from sales order detail, and under this, and you notice I'm up here in index test now, and execute it, and it's a clustered index scan. So we can look at, just looking at this, what we probably want is a non-clustered covered index that's on modified date, and that includes carrier tracking number, order quantity, and product ID. So let's do that. And if we do that to cover, and then we go back and run the query again, we drop the query cost by a factor of 20, and you can see it's an index seek. Okay, so we have this particular cluster, non-clustered index defined. So what happens if we go back and look at an update statement? And rather than, when I'm doing demos, I like to use begin transaction and roll it back after I'm through looking at the information. So that the information in the table doesn't really change going forward. So if we run this, all you can see is an update where I'm setting the order quantity multiplying by 2, and I'm adding 1 to the carrier tracking number. Look at the execution plan. I get, whoa, what is this over here? I get an index seek on the index I just created on IX sales order detail _ modified date. And you say, well, wait a minute, why is it using that index? Frequently I see a clustered index scan when I'm doing the updates. Well, in this particular case, because all the information up here in this update statement, order quantity, carrier tracking number, modified date, is in carrier tracking number, modified product, modified date is all in the index already. So, and notice the cost here is 1.2. Wow. As before, it was 1.04. No, that's not right. Anyway, so let's roll back the transaction. And now let's do a similar where I'm going to add an additional column that's not in the database, and that's unit price. And so if we begin this update statement here, okay, we get the clustered index scan like I thought we would. And why do we get it? We get it because unit price is not in the index definition. Let's roll that back. And if we just comment this out right there, try it again. Oh, I gotta also put a dash there. Try it again. And we look at the execution plan. We're back to our index seek again. So covered indexes can help performance by a considerable amount. So if you run a big update statement, you might want to look at it. And so you say, well, why does it need to either do the cluster index scan or the index seek? And it's because when you're in the transaction log, so that you can do the rollback, you need the old data as well as the new data. And that's why it works here. So let's clean up again, and let's go to our last example. And boy, my time is working out nicely, a lot better than I thought it was going to be. I don't need to do the big again here, but I mean, and I don't think I have these indexes in existence. Okay, so let's run another query. And I go back before I go any further. I got to go back and give credit to Penal Davey. He writes some unbelievable, neat articles, blogs, and I got this from him. And so I'll admit that this is not Mike Byrd's thing, but it has a issue with the index or the optimizer that we saw up above. And so let's go back and okay. So we run this and we run the select statement and we look at the execution plan. And you look at all this and you're going, well, what is all this table school aggregate? You know, because you're asking for up here in the query, you're asking for an average. So I expected the average. You have the scalars, you have the lazy pool, you have inner joins. And anyway, this is not like the query plan I would have expected to get. So pardon me, it just takes me a long time to sometimes get that. You get a query cost that's up around 2.5 or so. And you look at there and you have on sales order detail, you have 1248. But look at all these extra reads and that's a lot of reads. In fact, that many reads is roughly 10 megabytes for this particular table. And you go, wow, what happened here? This is not so let's create a covered index. And it's easy to figure out a covered index. Okay, so we're coming out of sales order detail table. So this is already part or the included in the clustered index, order quantity, product ID. And so let's come down here and let's have one on sales order ID, product ID, and we include sales order detail ID and the order. Probably didn't need to include this one, but so let's create that. Run the same query again. And now we get an execution plan that doesn't have all that extra stuff in it. We still have a sales order detail, and then we're hitting it with the non-clustered index, and we have an index scan on sales order detail, and that's because of the aggregate there and trying to find the average. So that's expected. And look at our query cost now is down to 1.14. And if we look here, we only had 614 logical reads, so a lot less in time. And you can see my answers there. So let's go back and just say you have another select query that you generate just an arbitrary another index on. And it's almost the same as before, but it's not. It's on product ID first. And we run the query again. And notice my title has second try there. And we run it again. And again, this is something that LW has done. And we're back to all that crud that we had in the first query before we added our first index. If you turn it off, let's drop the index, the second index, try again, and rerun the same query again. You get good answers. We're back to what we expect to get. So what is this telling us? Well, if you have indexes that aren't used, they could be hurting performance. Not only are they hurting performance from a maintenance point of view, they can hurt performance from a query point of view. Why the optimizer? Notice that the second index is not used anywhere in the query. You go back up here and recreate it again. Second try. And we come back and look at the execution. Oh, and then we run the query again. We got 5 minutes, I think, but I think that's enough time to finish up. We have all this stuff here, but if we look, it's a clustered index scan and it's on first try. We come down here and it's, where'd it go? And that's the only reference, but it's not, the index second try is not anywhere in this query plan. And if you want to get really into it and be geeky about it, you can go look at the XML plan and see that it shows up there. But anyway, so we've done all that. There's other examples here for I turn things on, turn things off, but it still comes out that if that second index is there, then you have issues. So with that, let's go back over to our conclusions. I'm hoping by now you're starting to get the idea that index column order can help or hurt you. And in one case, the Microsoft index suggestion was not necessarily the right one. I hope you now have seen an example where covered indexes can help update statements, and then unused indexes should either be disabled or deleted. I have in my utility zip file that I've included for download, I have scripts for missing indexes and unused indexes, and be wary of using them though, because they're only as good as when you last restarted the SQL Server. So I have lots of references. There's no particular order. If you're more interested, if you want to go out and look and do a lot of reading, there it is. I also want to put in a plug for a presentation I gave at Past Summit, self-tuning fill factor technique for SQL Server. Video and slides can be downloaded at the thing there. If you download the PowerPoint presentation, you get hold of it. Fill factor scripts are found at GitHub, username ByrdTX. It's been running for not quite 2 years, almost 2 years, and overall performance of the database, wait times have dropped 25%. I really want to thank you for the organizers and attendees.